Okay, moving on to question 5. It says state what is meant by the centre of gravity of an object. Okay, you just need to say the following. It's a point where all the weight of an object seems to act. Okay, that's extremely useful in physics, because if you have a complicated shape, say like a person on a seesaw, and you want to work out the moment that person exerts on the seesaw, that could be very tricky if you couldn't replace that person with a single point, which is the centre of gravity. So because there is this centre of gravity, you can kind of replace these complicated shapes with just a single point, and it makes it much easier to work out things like moments. Okay, it says part B, define moment of a force. Okay, you should say the following. The moment of a force is the force, or the applied force, times the perpendicular distance from the line of action of the force to the pivot. Let me just draw a picture to kind of illustrate what I mean. So if this is a seesaw and you have an object here, there's going to be, in this case, a weight force exerted down here. Okay, the line of action is this line along which the weight force acts, and then the perpendicular distance from that line of action to the pivot will obviously be, in this case, just this distance here. Okay, and a moment, you can think of a moment as kind of like a special kind of force. It's a special kind of force because it's a force that causes rotation. Okay, not all forces cause rotation, so you have to have this separate term, which is a moment, strictly to talk about a force that causes rotation. For instance, if I applied a force directly on the pivot here, there would be no rotation. Okay, so a moment is a kind of special kind of force that causes rotations. You can think of it like that. Okay, so moving on to the next part, we've got a baby's mobile toy here. We've got various objects, okay, and we're told that to take this as the pivot point, and we're given the weight of the objects. Okay, and then the first question that we're asked is, we're told before that the arrangement is in equilibrium, and it says state 2 conditions necessary for the rod to be in equilibrium. Well, the first one would definitely be that the net force has got to be 0. If there's a net force and it starts moving, it's definitely not in equilibrium. Also, the net moment must also be 0. We said a moment we can think of it as a special kind of force that causes rotation. Well, if there's rotations going on this mobile toy, it's definitely not going to be in equilibrium. Okay, so you get 1 mark for each of those points. Next part of the question, by taking moments about point A, determine the distance x. So it's asking for this distance here. Okay, how are we going to go about that? Well, we need to work out, it does say by taking moments about this point A. Okay, how you need to go about these questions is you need to set an equation up. Because it says it's in equilibrium, we can say that the anti-clockwise moments will be equal to the clockwise moments. Okay, which moment is causing it to go anti-clockwise? Well, that would be this. If we take the pivot point as A, it will be this moon, because that's trying to pull it down this way, which will obviously make it kind of rotate around this way, which is anti-clockwise. Whereas the star will kind of push down, and it will want to make this whole thing rotate this way, which is clockwise. And we can set up an equation where the anti-clockwise moments equals the clockwise moments. That will help us to solve x. Okay, so a moment, okay, if you remember a moment, what we just said before, it's just the force times the perpendicular distance from the pivot to the line of action of the force. So let's set up an equation here. So we've said that the anti-clockwise moments equal the clockwise moments. What's the anti-clockwise moment? Well, there's only one, and it's the force, 0.12 newtons, times the distance from the line of action of the force, which is along this way, times the perpendicular distance in this case, which is to the pivot, which is x. So all we've got to write is 0.12 times x, which is 0.12x. That's going to be equal to the clockwise moments. There's only one, it's the star. Force is 0.35 newtons. Again, the distance, the perpendicular distance from this line of action of this force to the pivot, is going to be this distance, which it doesn't give us, but it does give us this total distance along here of 0.5. And I hope you can see that 0.5 minus x, if you take x away from this 0.5, you are left with this distance. So we can therefore say that 0.35 0.35 times this perpendicular distance, which is 0.5 minus x. Okay, then all we have to do is multiply out the left side to start off with. So 0.35 times 0.5 is going to be 0.175, and then we've got 0.35 times minus x, which is just going to be minus 0.35x. If we bring this x term over, it's going to go from minus 0.35x to plus 0.35x. We can add that to 0.12x because they're the same terms, so that will be 0.47x. That will be equal to 0.175. And then you just solve for x, which is obviously just going to be 0.175 divided by 0.47. Okay, and you get 0.37 meters. So 0.37. So the thing to note about these problems is because it's an equilibrium, we can set the anti-clockwise moments equal to the clockwise moments. Okay, and it asks for x in this case, so we can solve for x. We didn't know any of the actual distances in meters, so we kind of had to set up this equation in terms of x and use a bit of algebra to solve it. Okay, so the last point in this question is determine the magnitude of the tension in the string attached to A. Okay, well, what's going to cause tension in the string? Well, it's going to be the weight of these objects. Okay, so you're just going to, all you have to do is just simply add the weight of this object to the weight of this object, because that's what's causing the tension, because we're told this rod is massless. So it's just 0.35 plus 0.12, so that's going to be 0.47 newtons. So 0.47 newtons. Okay, I'll end this video here, and we'll move on to question 6 in the next part.